Hello again. Now this is lecture 10, linear functions. And again, this is old, so the exam is not then or there. It is Thursday, June 4th. Online through HonorLock, and it will be open for 48 hours. So, now let's get on to lecture 10. Consider this. Consider job payment schemes. Job A has a variable rate of pay hour, while job B has a fixed rate of pay hour. Suppose that job B has a fixed pay per hour of, I don't know, $15 per hour. All right. So then job A, well, it's a variable rate of pay, so it's going to change every hour or so. So let's say it works like that. Job B, it's $15 per hour, right? So it's going to be changing by $15 each hour. Right? All right, so there's a way to describe both of these functions or describe these things. And we're first going to look at linear functions, which would be job B in the payment scheme. Sorry about that. All right, linear functions. The function f of x is linear if its average rate of change is constant, i.e., if you compute the average rate of change of f of x over any interval, you get the same value. So if you look at the average rate of change of some interval AB, don't care, just some interval, or, well, we want it for every interval, obviously. So every interval AB, then f of B minus f of A over B minus A is going to equal K, right? So for any interval we choose, we want that to be the same. The rate of change of the linear function is called its slope. Right? And the graph of a linear function is a line. Pretty straightforward so far, stuff we've seen. Linear equations are easy to construct and frequently used. Many relationships. I misread that. Linear equations are nice and easy, and that's why we like using them, especially in the real world, if we can. So let's look at measuring slope. We define slope as an average rate of change, but it also has a geometric interpretation. Rise over run. You might have heard something like that before. The slope between 2 points is the ratio of the change in y coordinate to the change in x coordinate. If the points are x1 and y1 and x2 and y2, then the slope between them is what? Well, let's draw a picture. We have, say, here is x1, y1, and this is x2, y2, y2. Well, then the slope of them, or rise over run, right? This distance is going to be y2 minus y1. This one is x2 minus x1. So it rises by this amount, runs by that amount. So this is going to be y2 minus y1, x2 minus x1. But we're dealing with functions still here, right? So y is equal to f of x. And so this guy becomes f of x2 minus f of x1 over x2 minus x1. And these are the same, right? Okay, so that's our measuring of slope. Pretty simple, pretty straightforward. So let's go on to actually evaluating some linear functions. So suppose f of x is a linear function with domain negative infinity to infinity. And if we suppose that f of negative 2 is equal to negative 4, and f of 3 is equal to 2, find two more values of f of x, right? All right, so there's a couple different ways you can go about this. Well, let's list the points here. So f of negative 2 comma 4, that tells us that one point is negative 2 comma negative 4. And f of 3 is equal to 2 gives us another point, 3 comma 2. So, sorry about that. So let's label this point x1, y1, and this point x2, y2. It doesn't matter which one you choose. Let's just pick it that way. All right, so what's the slope between these 2 points? Well, m is equal to 2 minus a minus 4 over 3 minus a minus 2. This is going to be turning into plus on both of these, so we get 6 over 5. All right, so think of it in terms of rise over run from the last slide, and we get that from this point, 3, 2, we go up 6, rise 6, and over to the right, because this is a positive 5. So I should say up 6 and then to the right 5, or over, right? So then another point would be well, up 6, so the y value goes up 6. So that's 8. And then to the right 5, well, if we take 3 and keep going to the right, we get also 8. And that's another point on the graph. Or another way to write that is f of 8 is equal to 8. 8, which is another point on the function. So if we want, we can do this graphically and say, okay, negative 2, negative 4 is here. 3, 2 is here. We get a line here. And then we can find another point on this line as well. So like if we chose, say, this point, and we did up 6 over 5, up 6, let's see, 4 to 2 over 5 would get us to here, right? And so another way of saying this is also the same as negative 6 over negative 5, yeah? Because here the negatives would just cancel. So we can also say, if we look at this point, negative 2, negative 4, and then we go down 6, and then left 5, we get another point. So that would be down 6, so that would be negative 10. Left 5, that would be negative 7 for the x. And that would also mean that f of negative 7 equals 10 is another function, is another point on your graph, or another value of f of x. Okay? So let's move right along to some graphical properties of slope. Well, let's look at this example. Graph the linear function passing through the point negative 3, 2, and 2, 0. Calculate the slope of that line. Well, let's sketch this out. Negative 3, 2 is right here. 2, 0 is right here. That's a little bit off, but it's fine. Roughly, it looks like that. Now, what's the slope between these 2 points? M is equal to, again, doesn't matter which, choose one to be your x1, y1, your x2, y2. So we're going to get 0 minus 2 over 2 minus 3. This is negative 2 over 5. Yeah. All right. So this is our slope, right? It is decreasing. It's negative 2 over 5. So our line is going downward from left to right. This is important because the sign of the slope tells us if the graph is graph of a linear function is increasing, decreasing, or constant. Increasing or decreasing. So if you have that your slope is positive, well, as we saw in the other examples, you get something like this, right? Some positive slope. It's moving upward from left to right. And in this example, when m is less than 0, we get something negative. So it looks something like that. Yeah. And then if your slope m is 0, that means it's a constant function. It does not change. It's a horizontal line. So that's not the best horizontal line, but anyway. The average rate of change between any 2 points on this line is 0. So it's constant. Right. So those are your properties of slope. Now let's get into some point slope form. If the paper actually works with me, we'll get into point slope form. There we go. So we frequently switch between f of x equals and y equals notation with linear functions. So that's a thing. So let's first work with y equals first and find out what the point slope formula is. Suppose that a linear function has slope m and x1, y1 is a point on its graph. Construct a formula for the function, right? So we're given that slope is equal to m, and we have a point on the graph is x1, y1. Yeah. So now let xy, this is an arbitrary point on the graph. This is an arbitrary point of f of x. So the average rate of change from x1, y1 to xy is going to be the following. We're going to have y1, or no. We're going to have y minus y1 from this point to that point. So this is our x2, y2, if you will. We're going to have y minus y1 over x minus x1 is equal to m, right? All right, now let's ignore that thing I have there. Multiply both sides by x minus x1. And so we get y minus y1, I'm jumping the gun here, is equal to m times x minus x1. Add the y1 over, and we get y is equal to m times x minus x1 plus y1. My lines are a bit crooked, but that's all right. But hey, we get point slope form, right? And so because we switch between f of x and f of y, another way to write this is f of x is equal to m times x minus x1 plus f of x1, right? This is the same as y1. This is the same as y. Same thing. Okay. So we found a formula. Let's put it to use in an example. Find the equation of a line passing through the points 1, 2, and 2, negative 2. Well, equation of a line that requires a slope. So let's find the slope between these 2 points. So m is equal to negative 2 minus 2 divided by 2 minus 1, negative 4 over 1, which is negative 4. Okay, so that's our slope. So we have a slope, and we are given 2 points. Right, so point slope form is y is equal to m times x minus x1 plus y1. It doesn't matter which one of these you pick. Choose either one. We're going to say y is equal to, I'm going to choose this one. M is -4. X minus 2 minus 2. So there you go. That's a pretty straightforward example. And also what we could have done, we could have graphed this. So this is what, 1, 2, and 2, -2. Right? Could have found the y-intercept up here, and we can easily see this is a very negative slope. So yeah, you can simplify this if you want, but this is the equation of the line passing through these points in point-slope form. Now, are there other forms? Yes. Are we going to go over them? Also yes. Right about now. So a slope-intercept form. Suppose that a linear function has a slope m and its y-intercept is b. Find a formula for the function. Well, we're going to use our good old point-slope form as well. Yes, we're going to do that. So we're going to look at it like this. Y point slope. Y is equal to m times, x minus x1 plus y1. Well, the point we're using is this y-intercept is equal to b. That gives us the point 0, b. So we have y is equal to m times x minus 0 plus b, or just mx plus b, which I'm sure everyone has seen before. Another way to see this is also f of x is equal to mx plus b. Or, okay? Okay, so we now have slope-intercept form. Let's go on to an example. Find the equation in slope-intercept form of a line passing through these 2 points. Well, you'll notice these are the exact same 2 points as last time. So from last time, we had y is equal to -4 times x minus, well, not -1. This is if we use, you know what, here. Y is equal to -4 times x minus 2 minus 2. That's what we had from the last example, right? It was slope is equal to m was equal to -4, and we chose this point, and we got this as our point slope form. All right, so let's simplify this out. And this is y is equal to -4 times x plus 8 minus 2, or y is equal to -4x plus 6. All right, so this tells us our slope and our y-intercept, and the y-intercept is going to be 6. Yeah. All right, lines are nice and easy and straightforward. So now let's go with another example. Graph the function f of x is equal to 3/2 x minus 3. Well, this gives us the slope-intercept form. So our slope, m, is equal to 3/2. And then our y-intercept is -3. So y-intercept of -3, that's 1 point. Now to find another, we use the slope, 3/2. So that is up 3, 1, 2, 3, over 2. Bam. Draw a line. That's a crooked line, but still draw a line. And there we have it. Nice little graph of the function f of x. Okay, let's go on to something a little more general. Not bad though. Slope-intercept example where g of x is equal to mx plus b. M is less than 0 and b is greater than 0. So Well, what does this mean? Well, let's look at the slope first. This means that if we go back a few pages, our slope is going to look something like that, right? It's going to be decreasing from left to right. Problem with what I've drawn here is that it hits the y-axis at a negative value. Well, this tells us that we have to be above the x-axis. We have to hit the y-axis above the x-axis, right? So an example of g of x that satisfy these conditions is something like this, right? The y-intercept is positive and the slope is negative, okay? Let's go with a few more examples. Find the intercepts of h of x is equal to 0.6x plus 9. Well, that's not good. Okay, had to fix the camera. So find the intercepts of this guy. Well, the y-intercept is the easiest one to find. The y-intercept is going to be 9, right? Because h of 0 is going to be 0.6 times 0 plus 9, which is 0. Sorry, that's just 9. And so we get the point 0, 9. Okay. X-intercept, not that it's hard, it's just a little unpleasant. X-intercept is going to be when h of x is equal to 0. So if we solve, 0 is equal to 0.6x plus 9. We get negative 9 is equal to 0.6x. And divide by 6 on both sides. Divide by 0.6, sorry. And we get that negative 9 over 0.6 is equal to x. This simplifies to 15, believe it or not. And so we get that the x-intercept is negative 15, 0. And there we go. Those are your intercepts for this function. Also, I went a little overboard because I forgot what we were doing. This is point slope form, right? Or sorry, this is slope-intercept form. So this tells us the slope and this tells us the intercept for y. So yeah, that was overboard. Didn't need that. We could have just jumped straight there. All right. Now let's move on to something a little more exciting, possibly. Or not. Horizontal lines. So the slope of a horizontal line, m is equal to 0, because y2 minus y1 over x2 minus x1 is going to give us 0 over x2 minus x1, whatever that is. But that's going to be 0. 0 over anything, 0 over a number is going to be 0. So the formula for this is going to be f of x is equal to m is 0. So this is just going to be b, right? Its intercepts are y-intercept. Well, that's obviously going to be at b. And then x-intercepts, we're not going to have any. That's if b does not equal 0. So for instance, if we look at this, pick any 2 points, x1, y1, x2, well, y2. As we set up here, difference in the y is going to be 0, difference in the x is going to be something, change is still going to be 0. In this case, our b is negative, and it never hits the x-axis, so it has no x-intercepts. So if b is equal to 0, then every point would be x-intercept. Okay, horizontal lines are fairly straightforward, fairly nice. So let's turn our heads 90 degrees and look at vertical lines. Well, let's see. Let's draw a vertical line. Point A, point B. Okay. If we look at the slope of this guy, we have y2 minus y1, x2 minus x1. This is going to be y2 minus y1. It's going to be something over 0. And that's bad. This is going to give us a slope that doesn't exist, right? Because you're dividing a number by 0, and that's bad. So the slope does not exist, and we don't even have a function. And so the formula for this would be x is equal to a for some a value. Call that a. So no matter what x you plug in, you're always going to have that output be the same. Wait, sorry, I said that backwards. For any y value that you try and plug in, you're going to have the same x value, x equals a. So let's look at x-intercepts. It's just going to be at a. We only hit this one point. And as for y-intercepts, same deal as last time with horizontal lines. We're going to have none if this a value does not equal 0, right? This does not hit the y-axis anywhere, so it doesn't have any. It only hits it if it is the y-axis. Okay. Keep going with some terminology and different kind of lines. Now on to parallel lines. Two lines parallel if they never intersect. So if we draw a line like that and another line like that, roughly, those are parallel. They have the same slope, but they have different y-intercepts. That's a y, not a v. Y. Different y-intercepts. So, I don't know, examples of this could be y is equal to 2x minus 5, y is equal to 2x plus 10. Yeah. Sure. So, parallel lines have the same slope but different y-intercepts. Okay. So let's move on to, again, another rotation of, not really, 90 degrees, but perpendicular lines. Two lines are perpendicular if they intersect at a right angle. So if we have, say, one line, and where's my other marker? Two lines. They intersect at a 90-degree right angle. So the slopes of perpendicular lines are opposite reciprocals. Reciprocals. I spelled that wrong. Anyway, spelling is my forte. So what do we have? Let's look at this guy. This guy is M1, and this guy has slope M2. In this instance, M1 is positive and big. Kind of. Could have drawn that a little bit better. But anyway, M2 is negative and small. So what it means by opposite reciprocals is suppose you have, well, it basically means this first. M2 is equal to the negative 1 over M1, right? Negative reciprocal. So suppose M1 is equal to 3/4. Well, then M2, let's stick with the colors. M2 is equal to the negative of the reciprocal of this guy, which is 4/3, right? If M1 is equal to negative let's do negative 3/5, then M2 is equal to the negative reciprocal. So it's going to be negative of a negative, turns it positive, and 5/3, the reciprocal. Yeah. This is your rule, if you will. This is the rule in words form. This is it in a more, I don't know, algebraic setting, if you will. So let's go on to an example of perpendicular lines. G of x is a linear function with g of 6 is equal to 8 that is perpendicular to the line that passes through the points 7, 11 and 10, 13. Find a formula for g of x. Okay, a little bit of information here. So first things first. Okay, so this gives us a point, right? This gives us a point 6, 8 on g of x. Yeah. Okay, so we have a point there. Now we need its slope. Well, we know that g of x is a linear function and it's perpendicular to the line that passes through these 2 points. So we need to find the slope of these 2 points and then take its negative reciprocal. Yeah. So what's the slope? Let's call M1, say, equal to slope between these 2 points, 13 minus 11 over 10 minus 7. This gives us 2/3. Yeah. So M2, the slope for g of x that we're looking for, is going to be the negative reciprocal of this guy. So that's negative 3/2. Yeah. All right. So 0.68 and slope negative 3/2. We get y for, or not y. Let's do g of x because we want g of x. G of x is equal to negative 3/2 x minus 6 plus 8. Yeah. So this is the point slope version of this. Let's go ahead and put it into slope-intercept form. And so we get g of x is equal to negative 3/2 x minus plus 9 plus 8. G of x is equal to negative 3/2 x plus 17. So this was our point slope form. This is our slope-intercept form. Either way, we find a formula for g of x that satisfies all these conditions. Okay. So let's look at linear function applications. So the slope of a linear function represents the rate of change, right? So it's the units. So we have points x comma y, right? So it's units y units per x unit, right? The slope is the average rate of change. So it's y units per x units. So if we look at this word thing, 3 weeks after starting a new job, you have so much money in your bank account, $925.75. After 9 weeks, you have more, $2,577.25. Calculate the slope of the function b of t for the dollars in your account after t weeks and state its units. Okay, so t is the weeks after. T is in weeks, and b of t is money in your account, right? In terms of dollars. So let's set up our points slash our function. So after 3 weeks, so t is, so we have, t comma b of t. Those are our points, right? So we have 3 weeks, we have this much. 925.75. And then after 9 weeks, we have that much, 2577.25. Right, those are our 2 points. So the slope between those two, we don't need that. Calculate the slope. So this is y2 minus y1, x2 minus x1. Doesn't matter which one you choose. So we're going to do it this way, 2577.25 minus 925.75 all over 9 minus 3. This gives us 1,651.50 over 6. And that reduces down to 275.25. What is this? These are just numbers. We need to state the units as well. This is dollars per week. So, right, so the change in Y, that's the change in money. What is the money? It's in dollars. So change in money per over change in Y, or change in X, in this case, change of T, which is weeks. So we get $275.25 per week. That's what this is telling us. Okay. Not too bad. And hey, that's not bad per week. Lastly, one more application example. In 2000, the United States emitted 6 billion tons of carbon dioxide in the atmosphere. In 2010, it emitted 5.5 billion tons. Construct a linear equation that models the annual emissions over time. Right, so what do we want to do? We want to find a function that models the annual emissions over time. Well, we need to make some rules here. So let t equal the number of years since 2000, right? We're only given information starting at 2000 and then to 2010. So we can't start at like 1998 because we have no information from there, right? Let's make C of t the number in terms of billion tons of carbon dioxide. Okay. So if this is what t is, this is what C of t is, then what are our points? Well, what are we given? In 2000, it was 6 billion. So at T0, years since 2000, that's 0 years, there was 6 billion, right? C of t is measured in billions of tons, okay? And then the next point, 10 years later, in 2010, it had decreased to 5.5 billion, okay? So we have 2 points. Let's calculate the slope between those two. So this is 5.5 minus 6 over 10 minus 0. This is negative 0.05. Yeah. So this also gives us the y-intercept. So we can use slope-intercept form, nicer and condensed. C of t is equal to negative 0.05 t plus 6, slope, intercept. And this represents decrease of 0.05 billion tons of carbon dioxide, ... per year. Right? So this is technically over 1, if you want to say. So it's negative, so it's decreasing by this amount. This was in billion tons, blah, 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 over years since 2000 and 2000. That's per year. Okay? Not too bad. Word problems are always a little bit of a pain in the neck, but you can get through them if you just take your time. So that concludes this lecture.